Welcome to my session here at SharkFest. My topic is Crash Course IPv6 and Network Protocols. Just a slide about myself. My name is Johannes Weber. I'm from Germany. I'm working as a network security consultant for a German company called TÜV Rheinland-Isig GmbH. And my core topics are these three next generation firewalls, VPN, crypto, and routing switching. So normally I'm working as a consultant at the customer, and we're selling some products to the customer. These are mostly firewalls and DNS and email load balancing stuff. I have three topics I'm interested in. These are IPv6, DNS, and NTP, and all of these topics I'm using in a secure manner. So when I'm at the customers, it's always, some of them, of course, using IPv6, not that many currently. Everyone is using DNS and everyone is using NTP, but you're not always thinking about the security. So I'm interested in using DNS in a secure manner, for example, that you cannot use DNS tunneling or that you're using DNSSEC for signing your authoritative zones. And NTP the same. Many companies are using NTP in a completely unsecure manner. They simply sync in their time to ntppool.org, but do not think about whether the time is reliable or not. I have a blog. It's called weberblog.net. I'm blogging almost once a week about network and security stuff, and my Twitter handle is webernetz. So what's the agenda? What's the motivation for this talk? I don't know what are you doing in your daily business, but for me, a couple of years ago, I had to solve some kind of problem. I was troubleshooting something with PCAP files, and I have had many unknown packets. Of course, these packets are not unknown to Wireshark, but are unknown to me as the reader. Because, and that's the agenda for today, some of them are related to IPv6. So even though you're not using IPv6 in your enterprise, you will see a couple of IPv6 packets in your network, and you possibly don't know what is this packet all about. And the same for network protocols. I think that for network protocols, many of you are quite familiar with. However, I have a couple of them just to say one to three sentences per protocol just to get an idea. So it's a crash course, so it's fast, it's no deep dive, and I'm skipping. So if anything is there that you don't know, raise your hand. If the answer would be too detailed, come back to me later on and we can talk about it. Normally I'm giving a 2-day workshop for IPv6 only. So it's quite hard to fit the complete IPv6 stuff in 30 minutes. It won't work at all, so it's just a rough overview. And you have never-ending acronyms. So especially for IPv6, you have this router advertisement, neighbor discovery protocol. You have quite new protocols and quite some new acronyms. Just one question. Who's familiar with IPv6 already? 1, 2, 3. I won't ask you any more detailed questions. I just want to get an overview. Okay, it's maximum the half who has seen IPv6. Okay. The Tracefiles, maybe you have downloaded them already. Download the zip file. You have 3 PCAPs in there. Please do me a favor and listen for the next 10 minutes to me and open the Tracefiles after them. I have 12 challenges, and for each challenge you will get a Snicker. So of course, every time the first one who answers the challenge correctly will get a Snicker. So during the next 60 minutes, I have about 12 questions related to the PCAPs. Okay. Let's start with the IPv6 part. This is a coffee. Someone made this photo back in the IPv6 launch day a couple of years ago. I will have a couple of slides just to bring you the idea of IPv6. It's just like a crash course before we are actually looking at the trace files, because you always have this chicken-egg problem when you're looking at the trace files, but you don't know what these packets are. Yeah. So I will just say a few sentences about IPv6. So IPv4 space is exhausted. This is not new to every one of you. IPv6 brings enough addresses, but it's not that easy, or I want you to dive in a little bit more into the address space of IPv6. At first, every client gets global addressable. So by default, IPv6 is global unique. You have global unicast addresses. That means every single device, your smartphone, your IoT device, your laptop, whatever you're using for IPv6, you have a global unique address that's different from IPv4, because Now we have end-to-end communication without state in the middle, so we don't have NAT anymore, which from a network perspective is absolutely perfect, because NAT breaks things and NAT is not a security thing. You're doing security with firewalls, with stateful firewalls, but not with NAT. So this is very good for IPv6, but you not only have addresses for your end clients, but you also have subnets for everyone. So, for example, when you're a company and you're getting a /48 prefix, then you have 65,000 subnets for your company that you can use. For a private customer, when you have a private ISP connection at home, for example, it's German, it's Deutsche Telekom in Germany, you have a /46. That means you have 8 bits for your subnets, so you have 256 subnets for your home connection. So this is really great for IPv6. You can even subnet your own home connection with IPv6. Almost only layer 3 changes. So that is, if you have a switched infrastructure, of course, you can use IPv6 with your old thumb switches or with your high-end switches. I don't care. You can simply use IPv6 above layer 2. And the upper layer protocols don't change either. So meaning when you're using DNS, IMAP, HTTPS, SSH, whatever, the upper layer protocols don't change at all. So it's mostly almost layer 3 that we are looking at when we're talking about IPv6. Of course, if you have custom applications with hard-coded IPv4 addresses, that's not a good thing at all. However, we are almost only looking at layer 3. We have no broadcasts anymore, but multicast. So this is an interesting point to talk about, because in IPv4 networks, at least the ARP request and the ARP response, or at least the ARP requests are sent to a broadcast. We don't have broadcast at all anymore, but multicast, which does not make the things easier. Because actually, when a switch receives a packet to a multicast group, what does the switch do? Yes, exactly. So the switch floods the multicast packets to all ports because the switch is not aware of any multicast listener states. So even though we don't have broadcast anymore, you have many, many multicast packets. When you're sniffing on any switch port, you will receive many, many multicast packets that are kind of broadcast in the layer 2 domain. IPv6 addresses are 128 bits long. They're hexadecimal. I think you all know that. We have 8 groups called hextets. So that's new. In IPv4, we call them octet. So now we have 8 groups. They are called hextet. We have the notation of address / prefix length. So we only have the concept of / notation, which is great. Again, in IPv4, you have these 255, 255, 255, whatever. Here we only have the / prefix notation, so you won't ever see an FFFF as the subnet mask or something like that. And we have 2 address abbreviations. These 2 IPv6 addresses are exactly the same. Sorry? They're not? Oh, shit. Oh, that's, no, oh, no, oh, no, no. This is, come on. So this is not good, of course. Yeah, first snicker, okay. Okay. So now the IPv6 addresses are exactly the same. There are 2 abbreviation rules. The first one is you can omit leading zeros. So when you're looking at this leading, can you see the laser point? When you're looking at the second hextet, it's 0 db8, it's exactly the same to db8. The other abbreviation rule is that you can omit consecutive zeros by writing : but this abbreviation rule can be used only once. So that is, here I have another part hextet with only zeros, but I must write it down as : 0 : Why? Because otherwise you couldn't reverse the process completely. If we have used here : again, then we would not know whether this cafe is at this part or at this part, because we can't do it exactly. So these are the 2 abbreviation rules. Many IPv6 addresses you will see in the trace files are really short, because they almost use one few hexadecimal values in the first hextet and a 1 in the last hextet. So this abbreviation is really shortens the address. And which is also new, subnets are always /64. So you have this 128-bit address. So exactly the first half, the first 64 bits are the network prefix. And the second part, the second 64 bits are the host identifier, the interface identifier, IID. So for IPv4, we have this variable length subnet masking shitty thing that you have in your DMZ. When I'm looking at the customer and you have a DMZ, you have tons of different net masks. You have a /24 here, you have a /30 for your small network, you have a /27, /28, and you're always thinking about what is the default gateway and what is the net mask. We have /64 period. This is great because it's much more easier for you to operate or to look at routing tables, to look at network traces, because you directly know which is your network part of the IPv6 address and which is the IM interface part. Some more addresses. The unspecified address, which is 0.0.0.0 in IPv4, completely abbreviated for IPv6 is simply : . So when you see this address, it doesn't even look like an address because you don't have one hexadecimal value at all. This is a complete valid IPv6 address. It's simply the unspecified address. Then we have another concept, which is completely new to compared to IPv4. It's this link local LL thing. That means these addresses are always starting with FE18 : . That means we have this concept of link local. Link means layer 2 link. Every IPv6 node that is connected to a switch that has an up, that interface is up, self-generates a link local address, which is not routable at all. It's only used for communication on the local link. Hence, it's called link local. So I'm not quite sure whether the guest Wi-Fi here has IPv6 or not, but when you're typing ipconfig/all or on Linux IP-6 show address, you will probably see that you have this kind of an address, starting with FE18, even though you're not using IPv6 in production. And the multicast part, this is crucial when you're investigating IPv6 packets, are starting with FFOO. Mostly you'll see multicast packets starting with FFO2. So again, what's new to IPv6? Every node gets a couple of addresses. Namely, it gets a link local address, as you might see on your device, and a couple of global unicast addresses. They called GUA. That's the global unicast address. So for IPv4, you're getting one single address and you're done. This is different in IPv6. You're getting multiple addresses per interface. So now here comes the point. And this is the one that this is now the part where the messages that you will see in the trace files are interesting. How is the client getting an address? So of course you can configure it manually when you're at the server, when you're at routers. Of course you're setting IPv6 addresses manually because you don't want any automated process behind it. You can use stateful DHCPv6. Stateful is almost exactly the same as we used for DHCPv4, for IPv4 addresses. That is, you have a DHCPv6 server, you're asking the server, hey, please send me out an address, you're getting the address and you're done. This is stateful DHCPv6. However, these two methods, manual and stateful DHCPv6, are not that deployed. For example, in your home connection, when you have a home router, you will not use these both, but you will use SLAAC. SLAAC, yet another acronym, is stateless address auto-configuration. So stateless, you don't have any state, you don't have any central component, you don't have any server that keeps track of the state, it's stateless. Address auto-configuration, so it automatically configures you an address. How is this working? And this is really the crucial part of IPv6 addressing. At first, your router that's present on the local link sends a RA, that's a router advertisement, with an /64 prefix. Meaning, I'm the router, I'm sending to the local network, hey guys, I'm a router, and I am terminating this /64 prefix. That's the route advertisement or router advertisement. Yes, one question, Christian?
Does he do it
Yes, so the question is whether the router sends these periodically. Yes, the default is every 5 minutes. So per default, every 5 minutes, plus minus a random value of a couple of seconds, you're getting this router advertisement, and the client, when it joins the network, can send a router solicitation asking a multicast address, hello, is there any router out there? And then the router immediately replies with a router advertisement. Then, and this is the interesting part, the client generates the second part of the IP address itself. So it generates the interface ID. I will come back on the next slide to see how the client does this. The third point, because you might argue what is when this self-generated IP address is already present on the link, then in the third part, the client sends a duplicate address detection, DAD, through the neighbor solicitation. So here we have another packet. Basically, the client generates an address, but does not use it immediately, but first sends out a message, is anyone else using this address? Nobody replied, okay, thanks, I can use the address. So he sends this duplicate address detection through a packet which is called neighbor solicitation. So we will see the neighbor solicitation again in a couple of slides. This process is called duplicate address detection. However, this packet is not called DAD, so you can't filter, you can't search DAD packets in your Wireshark trace file, which is getting a little bit complicated because you must search for neighbor solicitations to exactly get those messages.
Does this apply only for the /64 subnet or globally? I mean, it should take a while.
Of course, sorry, yes, this is only for the /64 subnet. So these neighbor solicitations is only to the local link. It won't be routed at someone else.
So potentially duplicates are possible?
Yeah, so in theory you have 64 bits. So in theory you have a space 2 to the power of 64, which is giant. So in the next slide I will tell you how the client generated, so then we will see that duplicates are, you won't ever see duplicates unless someone is attacking you. So I've never seen a duplicate for something that used the Slack process. You can, one side note, when you configure manually an address on a server or on a switch or on the router, then per RC standard, even though you configure the address manually, before the device assigns the address itself, it has to do the duplicate address detection as well. So in theory, if you have one router where you're just giving it the host ID ::1, and you have another router and you're giving it the same host ID manually, then the second router will first question that message, will get the other one router answering this message, and won't assign itself the address. So when you're manually configuring, yes, you will have duplicates.
But at the moment, we are just talking about a link local address.
Yes, we're only talking about, no, this is, sorry, okay, this is for the link local and for every other address. So we're basically talking here about the global unicast address. So the router sending out the global unicast prefix, which comes from the ISP, for example, for a home connection, and then your clients generating the addresses themselves.
And then generating also the neighbor solicitation message?
Yes.
For the global.
So we will have a look at the PCAP in a couple of seconds. So what's missing? What's missing is the DNS server. Of course, for DHCP v4, you're getting your IP address and the recursive DNS server. So until now, the IPv6 client has not get the recursive DNS server. So there are two ways for the clients to get the DNS server. The first way is through the router advertisement again. So in the router advertisement, there's an option for the DNS server. It's called recursive DNS server. So the clients know the IPv6 address of the server. The second one is stateless DHCP-v6. So there are networks where you must, after you have your address or even before, you must ask the DHCP-v6 server, but only for the DNS server. So the DHCP-v6 server will only reply with the DNS server, not with your address. This is called stateless DHCP-v6. So how does the client generate these host ID addresses? That was the question a couple of seconds ago. There are three ways. Normally, the IID, so the interface identifiers, are generated through a process called EUI64, that is the MAC address, split into two parts. while inserting these FFFE in the middle. So this is basically the MAC address. So,
it flips the local bit too.
Sorry?
It flips the local bit in the first byte. When you use the MAC address, it flips the local bit in the first byte.
Yes, exactly. I omitted the details, but you're correct. So based on the question, are there any duplicates on the network? No. Because if you have duplicate MAC addresses on your network, you have another problem anyway. So in the real life, you won't see duplicate MAC addresses on your network. I know that even for virtualization also, some vendors are using the MAC address more than once, but in the perfect world, they're not. So you won't have any duplicates on your network. The second thing is the host can generate those addresses stable but opaque. That means it's stable but looking random. So that is when you're shutting down your computer and you are rebooting it, it will get the same address, so it's stable. But because the first two are stable, that means you can track the IP address, the host ID. So when you're moving your computer to different locations, you will almost always get the same ID, host ID, but with different network prefixes. So you can trace back to the client, because when you're always visiting google.com or facebook.com or whatever, then they can easily see that you're the same MAC address, so you're the same computer. So we have something called temporary addresses. These are the privacy extensions. There's some movement in the RFCs whether this is good or whether this is bad, or whether we should use them or whether we should not use them. However, most of the operating system currently using these privacy extensions additional to one of the first two methods. So when you're looking at your client in an IPv6 enabled network, you have one link local address. You have one stable address, which is either done with the MAC address or randomly but stable. And you have a privacy extended temporary IPv6 address in the same network, which you're using for outgoing connections. And this has a timer, timestamps and lifetimes, so maybe every 8 to 24 hours you get a new privacy extended address, while the other ones stay alive for current connections. So when you have a device that has a couple of days on the same network and you're looking at your interface, you will see that you have by far more than one IPv6 address. So what's the problem? Now we're coming to the Wireshark part. So this was the address assigning part. Now we're coming to the Wireshark part. What is the problem with all of these messages? Mainly the router advertisement and the router solicitation and these duplicate address detections. All these messages are within the ICMPv6 suite. So ICMPv4 for IPv4 networks was basically ping. You had echo request, echo response, and you're done. You could filter ICMP on your firewall, which points to the ISP, to the internet. You could block it completely, and everything worked. You could even block ICMPv4 on your local link, and everything worked. Here it's completely different. You need ICMPv6, and it's by far more than ping, because all these basic messages are within this ICMPv6 suite. So there's a suite that's called Neighbor Discovery Protocol, another acronym NDP. So all of these messages I was talking about are within this Neighbor Discovery Protocol. However, again, you won't ever see this NDP on a Wireshark message, because the protocol itself is not called NDP when you're filtering it. These are all ICMPv6 messages. So when you're filtering, you must use these ICMPv6.type equals, and then the type number. Of course, this is not a correct here. You must use only one of these numbers. So for example, the router solicitation, which is, hello, is there any router? Has number 133. The router advertisement, when the router says, hello guys, I'm your router, you can use me, please generate your address, is 144. And we have the same for neighbor solicitation in a neighbor advertisement. Neighbor solicitation is, hey, I'm searching for a neighbor with this IPv6 address, and then the neighbor answers with a neighbor advertisement, hello, you're searching for me, this is my MAC address. So you must use these filters, these display filters, when you're using Wireshark. And for DHCPv6, it's a little bit easier because it's simply DHCPv6. So what I'm using is coloring rules for exactly these. So that is, for example, my coloring rules look like this. So the third line is the router solicitation, router advertisement. The second line is the neighbor solicitation and the neighbor advertisement. And how can you see the duplicate address detections? The duplicate address detection are again a neighbor solicitation, but are sent from the unspecified, from an unspecified source address. So this is the only way that you can see that you have a duplicate address detection message. Applying these rules, this is exactly the same view. You must not look at the details, but just to get an idea. On the left-hand side, I filtered for IPv6, and everything is IPv6. And you will see them in your productive networks. You will see hundreds of IPv6 messages. These are my coloring rules, and you can easily see that I have some router advertisement, that I have one single, so this light green message here is my duplicate address detection. It was only present once. That's the one who has a source address of : because it's unspecified. And I also have some other IPv6 messages like this one, so this in fact was a ping. Yeah. So, but now with these coloring rules, I can differentiate between crucial IPv6 messages and ping. So we are coming to the first trace. So please open the first trace. It's called first and then something. Knoppix Telekom. I took this packet capture a couple of years ago. I used my home ISP connection from Deutsche Telekom, and I used the Knoppix, that's a live Linux computer, and I took this packet capture without any other devices in the network to almost have no noise in this packet capture. And in this packet capture, you can see that you have an IPv4 connection, and I'm pinging something, and then I have an IPv6 connection, and I'm pinging something as well. So when you're looking at this packet capture, we will look, for example, to the router solicitation and to the router advertisement. So these are, I will show it here. So number 8. Just want to make it a little bit smaller here. Number 8 is the router solicitation, and number 9, again, we have a router solicitation. So basically, the router solicitation is sent to a destination address of FF02::2. This is the multicast address for routers, so that every router listens on this multicast address to accept these router solicitations. And even more interesting is the router advertisement, which is message number 12. So it's an ICMP, of course it's an IPv6 packet, it's ICMPv6, then we have the type of 134, and you can see we have a prefix information. So we have a /64, because we are only using /64s, and we have this prefix. So this is the prefix that the router has told to the clients, I'm terminating this prefix, please generate your addresses. Then a client really uses this information and generates an address, but sends a duplicate address detection, which is message number 21. I've made it light green. So here you can see this message is sent from the unspecified source to a multicast address. I will explain you this multicast address in a couple of seconds. Asking for a target address. Asking, is anyone already using this IPv6 address? Since no one replies, a couple of seconds later, here you can see that the client actually uses this address.
So,
yes?
the client is expecting no answer to this.
Exactly. So the client has a timer. When there's no answer within 2 seconds or something like that, then the client expects that this address is not used.
So if we see a neighbor solicitation and no answer, we can expect
Exactly.
that the client will use that.
Exactly. So when the client doesn't get any answer, he uses this address. And finally, we have the DHCPv6. You can simply filter for it. So here, the client, again, asking a multicast group. This multicast group is the multicast group for all DHCPv6 servers. So no broadcast here. Yeah? For IPv4, DHCP before you would use you would send the discover message from DHCP to a broadcast group here using a multicast, and then the DHCPv6 server is replying with the IP address of the recursive name server. First challenge: what are the flags from the prefix information? So please have a look at the route advertisement, message number 12. What are the flags from the prefix information? Because, of course, in the prefix information, you have some flags, you have some lifetimes. Yeah, question?
Other configuration set.
Okay, so it's the... Oh, okay. Other configuration router preference? MTU. No, I'm really searching for flags. 1 or 0. On-link. Yes, so this is the correct answer. So the first Snickers. I'm not quite sure whether I should throw it. I will throw it to the there. Yeah, it's better as it would land in your face. So the question here was, what are the flags from the prefix information? When you're looking at the route advertisement, then you have flags from the route advertisement itself. These are the O flag that you set first. But I was asking for the flags within the prefix information, and here you have flags again. And these flags are on-link and autonomous address configuration, meaning you're using this A flag to tell the client that the client shall use this prefix to really generate the address itself. So be careful, you have multiple times these flags section within a route advertisement, because you have it once for the route advertisement at all, and then for every prefix information option, you have flags and lifetimes again. So, but your answer was correct. So the flag here is the O flag and the A flag.
So if I have different, more than that 64-byte prefix,
you can have multiple /64 prefixes per route advertisement. So when you have a router and you're connected to two ISPs, and both ISPs are giving you some IPv6 address space, then you can, maybe you should not, but you can use a couple of prefixes within one single route advertisement. So, and then you can tell the clients, here I have a couple of prefixes, but please use this one for generating your address, for example. The second part of IPv6 is, so this completely route advertisement and the Slack process of generating the addresses, this is really the crucial part, because you will see lots of IPv6 messages. No, I think you have a clue what are these messages all about. So the other, and that's the second part of the IPv6 part, is the link layer address resolution. So that's basically ARP in IPv4. When I have an IPv4 address that I can see which is on my local link, because I have a subnet mask and I see that I must not use the default router, but I can get it directly. So I directly want to send my Ethernet frames to this local connected IPv4 address. I'm sending an ARP and I'm getting an ARP response. Here, for IPv6, this process is called neighbor solicitation. So that's exactly the same message we have already seen. It's an NS, neighbor solicitation. Sends to a special multicast address. This is not funny, because for IPv4, you had ARP sent to the broadcast, and someone replied. Here, we have this example. This is the IPv6 address that the first client wants to know which MAC address he has. And he sends this neighbor solicitation to this multicast group, which starts with FF02 and ends FF with the last 6, and here I don't have this spelling error again, which ends with the last 6 hexadecimal values from the actual IPv6 address. So when you're looking for neighbor solicitations on your network, you can not only filter for this type of neighbor solicitations, or if you filter it like this, then you have hundreds of different multicast destinations where these packets were sent. And this is fully correct, because for every IPv6 address, there's a unique, or there's an almost unique multicast address. This multicast address is called the solicited node multicast address. So it's one of these buzzwords, solid-sided node multicast address. So, okay, and the target then answers with a neighbor advertisement. So when I'm asking to this multicast address, hey you, what's your MAC address? Then the target is answering me again with for the first time with a neighbor advertisement. And this neighbor advertisement then carries the MAC address because we want to know the MAC address. So it's IPv6 type, we have already seen it. So at the trace file again, please look at the first PCAP again. We have a neighbor solicitation and a neighbor advertisement. These are messages 5.3 and 5.4. Here we go. So we have from a source, FE18::1, this is the IPv6 address of the router in my home network. He asked to a destination address the solid-sided node multicast address. It's a neighbor solicitation, IPv6 type 135. And it's asking for a target address. That's the address he wants to know the MAC address. And immediately after that, the global unicast IPv6 address is answering with a neighbor advertisement, 136. The target address is, again, the address it was asked for, but you have a link layer address that's basically the MAC address of the client he was asked. Interestingly, in the solicitation, we have this IPv6 option source link layer address, which is quite a good thing, because for IPv4, when two clients want to communicate each other, the first one sends an ARP, what's your MAC address, and sends the packet. Then the second one wants to answer this and must send an ARP request again. Please send me your MAC address. So you have this ARP process, you have it twice. Here you have it only once, because the first node who starts the connection asking for the MAC address sends its own source link layer address in the question. So that the other part who will answer the packet must not start this process, neighbor solicitation, neighbor advertisement again. So I'm running a little bit out of time.
IPv6, before, the other side must not do it too. It does, but it must not. It must not, it has not to do it. It does.
Okay, so I'm not quite sure. However, here for IPv6, you'll need this process only once. So again, no challenge here. So yeah, so these are the messages that are crucial to IPv6. So now when you're looking at the trace, you have some more annoying stuff, which are basically all related to multicast listener things. So you have this MLD, that's the multicast listener discovery, that's another protocol. These are a couple of IPv6 messages. And these multicast listener discovery messages are related for routers, because every client, every IPv6 node sends a couple of these multicast listener discovery messages to the network saying, hey, I'm listening to this multicast address, and I'm listening to this multicast address, and by the way, I'm listening to this multicast address again. However, these messages are not needed at all, because your router is not interested in your local layer. So the router is not interested in listening to multicast addresses for you, because the address resolution takes place only on the local link. As of today, the switches are not aware of these multicast listener reports as well. So in theory, you could use some functionality, for example, multicast listener, I don't know the name. So you have a feature on a switch to listen for this multicast listener reports, so that the switch won't flood multicast packets to all ports, but only to the ports he knows that someone is listening. So this is a feature, plus the recommendation is not to use it, because it's not simple and the switches are not made for listening to so many packets. So in fact, you have a couple of more IPv6 types that are all related to this multicast listener stuff. Filter them out, because you don't need them. What I'm doing, I'm using another color filter. This is this one that simply makes it with a white background and a light green foreground, so that, yeah, I'm not irritated by these messages. Okay, to sum it up for the IPv6 part, IPv6 is absolutely crucial. You have a couple of messages router solicitation, route advertisement, neighbor solicitation, neighbor advertisement. You have the duplicate address detection, which is a neighbor solicitation sent from the unspecified address. You have ping, of course, with an IPv6. You can ignore all this multicast listener stuff. You really don't need it. There's no use case for it currently. The clients are sending them, but you don't need them at all. And you have DHCP v6. So just for 1 or 2 minutes, please open the second PCAP. So the second PCAP, too long didn't read, is nothing to see here. Why? In the second PCAP, I made this PCAP within, I think, 8 different upper layer protocols. This is DNS, HTTP, HTTPS, IMAP, SNMP, and then 3 more protocols that are used from a network security guy who's managing the networks, namely SSH, SNMP, and ping. And the complete trace sits above IPv6. So please use this PCAP just to click a little bit around so that you can see that you're a little bit familiar with these IPv6 addresses. Unless you don't know them, you won't use them. So just click a little bit around and you can see that DNS is exactly the same as for IPv4, but it sits on IPv6 addresses. HTTP is exactly the same, ping is exactly the same, but only the layer 3 changes. So I won't use this PCAP here in more detail. I have just one challenge for you. What's inside the HTTP answer? So there's one single plain text HTTP session, TCP stream, in the second PCAP. Please open it, have a look. So there's one get and there's one answer. What's in this HTTP answer? Sorry?
Better flavors of the script.
Flavors of the script? What script?
That's what the HTTP content is like.
So what's in the HTTP? Please, can you read the first line of the HTML, which is inside this table border? Yeah, exactly. That's correct. One sticker for you. I won't throw it. So just a side hint: when you're using the second PCAP here, and you're finding the HTTP, when you're doing the normal follow TCP stream, then it looks like this. I don't know, can I? Okay, here. Then it looks like this. So you have your request, but the response is gzip compressed. So you can see only this one. But when you're using not following TCP, but following HTTP stream, you can only click this when you're on the HTTP packet and not on the TCP packet. Then it's decoded. So, and then you can see that simply it's a table which is inside this HTTP answer. Yeah, exactly. Any questions so far concerning IPv6? No. Again, you can come later to me to ask any more specific questions if you want. So that was the first part of my talk. The second part is for network protocols. So again, network protocols, you will see them quite often when you're doing a packet capture on your server, on your client, on any intermediary devices. You will see a couple of protocols that are used by network devices, by switches and by routers to communicate with each other or to communicate with a network management station so that an admin has configured certain protocols to get information, to send information. So I have, it's the third PCAP. You can open it. It's called in third CCMP switch final something. In this PCAP, I have about 22 different protocols. I've made a packet challenge 1.5 years ago. I will give you the link for the packet challenge if you're interested any further. What I want to present now in the next 20, 30 minutes are 10 protocols that are quite common from my perspective when I'm at the end at a certain customer. 5 of these link layer protocols, or 5 of these are link layer protocols. That is, they are above Ethernet but not IP. and 5 more are based on UDP. So it's not DNS or HTTP or SNMP, so it's no application, no layer 7 protocols, and it's not RIP or OSPF or BGP, so it's not routing protocols, but these are all protocols that are run on the switch or by routers, but not kind of these. So the first one is the spanning tree protocol. I think you should already heard of spanning tree protocol. Spanning tree is a protocol that prevents loops within switched networks. So if you have, let's say, 4 switches and you're connecting them to a loop, then in theory, if you don't run spanning tree, then you'll have a loop and your network is fully congested because, yeah, some packets are enough to bring down the switch data planes. So spanning tree calculates a path from the root bridge. So spanning tree is run per VLAN, and the default today is rapid spanning tree. You can also put a couple of VLANs together and run MST. However, for some smaller companies, this is still the default. You have something that is called a root bridge. In fact, it's a root switch, but for historical reasons, it's called a bridge. The root bridge is the central point, so you're handing out a priority that it gets the root bridge. And then this root bridge calculates path among the complete network to find loops and to block ports so that your loop, in fact, is blocked. And if you rip off another cable and you don't have any connection at all anymore, so then it will forward the port, so it will delete the blocking mode. So the interesting point here is spanning tree by default sends an hello packet every 2 seconds out on every port per VLAN. So when you're taking a packet capture on a switch port where you have hundreds of VLANs, you will see about 200 spanning tree packets per second. Okay, it's every 2 seconds, so we'll see 100 spanning tree packets per second. So this is the I/O graph from this third PCAP you just opened. You can see the black line, which is the upper line, is the overall packet rate in this complete trace, and the red line is the spanning tree. So when you're scrolling a little bit in Wireshark, you will see that almost 50% of all of these packets that are within this trace are spanning tree. And this is exactly what I'm seeing when I'm troubleshooting a small problem at the customer. I don't have gigabytes of PCAPs like Jasper always handling with gigabytes of PCAPs. That's not my scenario. I almost have some small DNS problems or HTTP proxy problems. So when I'm connecting to a client, I'm always getting spanning tree protocol packets. And this is good. Do not disable spanning tree on user ports. So you could think about, well, I have a user connected. I don't have a switch connected. I can disable spanning tree. Please don't. Because the users are kind of stupid, so they will use their own switch or they may use 2 cables, plug them into the wall, and then you have a loop from user ports. So the recommendation is to not disable spanning tree on the switch facing 2 user ports, but to have it active. Here are some more keywords that I won't read out. If you want to Google it or whatever, then these are the couple of keywords that are used for spanning tree. Interesting part, spanning tree is not needed anymore in software-defined networks today because you have a single brain. Okay, it depends, but in common scenarios, you have a single brain, so your single brain decides whether it's blocking or forwarding path and not the switches independently. Yes, there are some functions, but yes, exactly. So these BPDU guard is listed there. So there are any details. It's just to give a rough view that when you have a packet capture and you're seeing a spanning tree protocol packets, that you have an idea what is it all about. Here's my challenge. What is the root bridge identifier for VLAN 40? So please find a spanning tree packet from VLAN 40. So you can use the display filter STP. Then I have a column for VLANs. Find a spanning tree packet that's from VLAN 40. And I asked for the root bridge ID, which is used for VLAN 40. Yes, in the back. Sorry? This is correct. So the bridge identifier, you can see the spanning tree protocol, and then you have a couple of fields in there, and you have a port identifier and a couple of more, and then we have the bridge identifier and the root identifier. And the root identifier, this is the ID of the current root bridge for this VLAN 40. So, correct. I will just bowl it to you. Curling. Okay, so for any protocol that's coming into the next minutes, I have one challenge. So the second protocol here is Cisco Discovery Protocol. This is Cisco proprietary. However, from my perspective, many customers are still using Cisco devices, at least in some points. So Cisco Discovery Protocol shares information about directly connected devices. So CDP is not routed, it's even not switched over switches, but when you have a router and a switch, or if you have a switch and a switch, these packets are only sent between the directly per cable connected devices from port to port. And for example, they are saying, hey, I'm switch, I have this platform running, I have this operation version, I have this MAC address, and so on. So CDP, from a networker's perspective, it's quite good, because when you have a third-party company who shall plug in some switches and you're not quite sure whether they have plugged in them correctly, you can go to your switch, you can show CDP neighbors, and you can see to which port they connected which switch or router or whatever. So the keywords here are TLV, type length value, because you can have different values, and CDP spoofing. Because from an attacker, of course, can spoof these CDP packets. So when you want to attack someone, maybe you can start by using CDP spoofing. Here's my challenge. What's the IPv4 management address of the client CCNP Lab S1, which is a switch? Yes? 192.168.121.10. This is correct. Sorry, somewhere there. So when you're using CDP as a filter, you can see these CDP messages. Then in the info column, you can see that there are two devices sending this CDP, which is quite common because, in fact, I took this packet capture sitting between two devices. So exactly both of these devices are sending a CDP and no other device, because I was just capturing on one link. So looking at the CCNP switch 1, Cisco Discovery Protocol, you have a platform, you have a port ID, and so on, and you have a management address, type IPv4, and this is this one. Exactly. So since we're not all running Cisco devices, you have something vendor neutral for almost the same. This is the link layer discovery protocol, LLDP. That is a vendor neutral version for sharing layer 2 information. So it's almost the same as CDP, but it's vendor neutral. So for example, I'm working with Palo Alto network firewalls. You can configure LLDP, which is quite nice, because in the GUI you can see to which other switches or routers you are connected when they are sending LLDP messages as well. So the keyword here again is information gathering. When you're an attacker or when you're a network guy who simply does its job, you can get a couple of information. The challenge, what is the IPv6 management address of the CCNP Lab S1 switch? So maybe you can read out just the last 6 10, yes?
The last 6, that's
10, yes. So it's basically, it starts with 2003, 51, 62, 6012, genau. So the fun fact here is that is my prefix. So for a certain amount of time, this was my IPv6 prefix. So, and I know it completely in my mind, so it's 2003, 51, 6012 when you're looking at it. So this is my prefix. I have this prefix for a couple of years. For all of these persons who are saying, oh, I can't remember IPv6 addresses, this is not true, because I have one prefix. It's 2003, 51, 6012. The fourth hextet is my VLAN ID that I use to distinguish my subnets. Yeah? And which is 121, I think, in this one, yes. And then for the last set for the interface ID, I simply using a kind of count or something like this. So it's not that complicated to remember IPv6 addresses because you have your one and only IPv6 prefix. So when you're doing it live here, just want to have a look at the time. Okay, it's good. LLDP. So there's only one device here sending LLDP messages, so you can pick up any of it. You're looking, you have capabilities, you have software running, you have a management address, which is IPv4, and you have another management address, which is IPv6, and here you have my prefix, 2003-516012, and so on. Yes. So again, we are going Cisco proprietary. We have the VLAN trunking protocol, VTP. The display filter is VTP. So this protocol propagates VLAN information, VLAN definitions. That's basically the ID of the VLAN and the name. Why do you want to use it? Because when you have hundreds of switches and you have hundreds of VLANs, and you're plugging in the 101th switch, you want that this switch knows of any of your VLANs, and you must not configure them manually. So we can use VTP for that. We have 3 different versions. The recommended is version 3. However, in reality, version 2 is almost used at our customers. So we are not recommending this. However, they're doing it. The keywords are configuration revision number and a few others. The configuration number here is crucial because this VTP process only uses the information with the highest configuration revision number. So when you have a network, 100 of switches, 100 of VLANs, and you're on the revision number, let's say 100. And you have an old switch from another company which has revision number 200, and you're plugging this switch into your network. This switch will completely flood your complete infrastructure with the VLAN information it has, because simply it has a higher revision number. So please be aware when using this protocol. However, it has many advantages because for companies that have hundreds of switches, it's quite easy. However, it's a Cisco proprietary. Here's my challenge. What's the name of VLAN number 10? So please search for a VTP packet. There are some summary advertisement and subset advertisement. I think you must click the subset advertisement. And then to find the VLAN is not that easy because there's a field called ISL VLAN ID. And this ID is not decimal, but hexadecimal. So you have to search for the hexadecimal value of 10. What's the hexadecimal value of 10? That's an A. So please search for the entry. So what's the name of VLAN 10? So in this VLAN trunking protocol, in the subset advertisement, you have a couple of VLAN informations. Do you have an idea? What's the name of VLAN 10?
I also have a Snickers.
You already have a Snickers? Someone else who does not have a Snickers? Correct. So let me just find it as well. VLAN, no, what is this? Here, VLAN 10, it's the VLAN ID A, because it's hexadecimal, and the name is VLAN 10 und sonst nix, which is basically something like and nothing else in German. So thanks for the Snickers. I will just give it to you that way. Please hand it out. Thanks. So another protocol which is quite common, not only for routers and switches, but also for servers and for other devices, is the link aggregation control protocol. So now the acronyms are getting longer, so the headline doesn't fit the complete protocol number. The filter is LACP. LACP negotiates an automatic bundling of links. So it is, you want to bundle a couple of physical links together to have more bandwidth in the communication between a couple of switches or from switch to a server, for example. So there are a couple of names. Cisco calls it Ether channel. Other vendors call it trunk. which is not that easy because for Cisco naming, a trunk is a VLAN trunk. Others call it aggregated link group or whatever. It's doing almost the same. It bundles a couple of physical links to one logical link. And you're using it not only for switches, for example, VMware servers, they are able to do LACP as well. So there are two flavors of the protocol, slow and fast, slow protocols or fast protocols. And the default is slow, which sends an hello packet every 30 seconds, which is quite okay. And the fast one, of course, is faster in negotiating the link. It's sending these packets every 1 second. For example, the old Cisco router switches can only do the slow protocols. The Cisco Nexus switches can also do the fast ones. So the keywords here are, you have an active and a passive mode, so you can decide who of the two involved parties decides whether they are doing a bundle or not. Then you have a system and a port priority for some kind of reasons. In almost all sections, it's good when you're leaving them by default. So the challenge is, LACP as seen from the actor with this MAC address. What's the partner port priority? So you will see, as I sniffed my packet capture between two switches, I have only two actors sending LACP messages. So as seen from the actor with this MAC address, the last two values are 5A80. What's the partner port priority? Yes? 32768. This is correct. So, yeah, in fact, it's default correct. So when you're looking at LACP, you're looking at the actor with the 5A, for example, this one. Then you have many ideas, and you have the partner port priority, which is exactly this value. Yes, correct. So the last row is quite good in getting some Snickers. Next protocol. We are Cisco proprietary here. That's the hot standby router protocol, HSRP, HSRP. That's a protocol for redundancy of the default gateway. So when you have redundancy for routers, then you are talking routing protocols such as BGP or OSPF or IEGRP, for example. Then your routers can have your forwarding path. However, for the last mile, for the client has only one single default gateway on a local link. So when you want to have two routers and you want to have redundancy that when one router fails, the client can simply forward their IPv6, IPv4 packets to the same IP address, you must use something like this. So this is not a complete HA pair. When you're working with firewalls, as I do in my daily business, I have two firewalls in an HA setup, and I have one active and one passive firewall. When the active firewall fails, the passive firewall becomes active and immediately takes the complete brain and does everything. This is different. Here you have two routers that are completely active, and per interface, so per layer 3 subnet, you must configure HSRP, and the router with the highest priority then is the virtual router with the virtual IP address. And this is the IP address you should use on your clients as the default gateway, for example. So it's not an HA pair, it's only virtual IPs. We have a standards-based alternative to this HSRP. This is called VRRP. So there are other routers from other vendors, or even firewalls, or Infoblocks, DNS servers, for example. They're doing their redundancy via VRRP as well. So this is the vendor-neutral, the standards-based version. However, as I took the PCAP, I had only configured this as HSRP. Okay, challenge. What's the virtual IPv6 address for the HSRP group 1 to 7. So when you're filtering for HSRP, you will see that HSRP is running for both protocols, IPv4 and IPv6. When you're clicking at any of the IPv6 protocols, you will see, you can find out the virtual IPv6 address for this group. What IPv6 address is it? 7F at the end. That's correct. Thanks. So when you're looking at the PCAP, we are filtering for HSRP. Then we have some IPv4 and some IPv6 packets, Cisco, hot standby. We have a group, and here we have the virtual IPv6 address that it's used by the clients, that shall be used by the clients. Because when you have two routers and you only have one client.
But why don't you use any cast address?
Because it's another burden to say. So in fact, you can do it, but then you don't have a clear path. Maybe both routers are answering. You have another technology that needs to be troubleshooted in case of an error. So normally you're using something like this. Okay, I think I have 4 more protocols and at least a couple of minutes left. So syslog. Syslog, I think this is quite known. Syslog is a message logging to a central server. So that means it's not only for routers and switches, but also for firewalls, for any antivirus, advanced persistent threat appliance, DNS logs, whatever. You can send syslog messages to a central server. We simply call it the syslog grab, so the syslog grave, because you have tons of text messages. Nowadays we are using ZMs or something like Splunk, which is not in fact a completely ZM, but it simply aggregates all this information together. So syslog is part of UDP. So we are now using IP protocols for the remainder of this session. It's UDP port 514, and it's plain text. So by default, syslog is plain text. You can use syslog with TCP to have it reliable, because normally it's UDP based, so when your syslog server is not listening, these syslog messages are simply gone. When you're using TCP, then you're getting an error messages, and the client can wait for a couple of minutes until the syslog server is reachable again and can then send its syslogs. And you can use TLS, which is in fact recommended, of course, because you don't want to send your network information error messages with plain text. However, UDP port 4514 is almost the default. Keywords are facility. You have different facilities, and you have severity levels 0 to 7. Emergency is the highest level, is the O. The 7 is debugging. Debugging means you're sending almost everything. Yeah. So the challenges, please filter for syslog. Which interface? Interface, there's an R missing. Which interface changed the state to up? Gig 02, which is correct. So I think again it's the last, again it's the last row. This is correct. When you're searching for syslog, and and then you can look here, you have some informations, and here's one that changed the state to app. So basically you can follow the UDP stream, and this is exactly the syslog messages that the Cisco switch router, I don't know, sent. Exactly. The network time protocol. So this is not related to network anymore, but it's used on almost every device. Basically, it's a clock synchronization. So to be more precise, it's not a synchronization process, but a client-server process. So normally, your NTP client, which is any device that you have, it's a firewall, it's a router, it's a switch, it's a server, whatever, it's an IoT device, gets the clock from a server. So it's no synchronization in both directions, but it's getting the clock. It's using UDP port 123. You have this concept of stratums. Stratums, I don't know how to pronounce it in English, to be honest. Stratum. The stratum 1, for example, means that you're synced to an external source, clock source such as GPS or DCF77, which is a radio clock in Germany. If you have one stratum 1 server or 2 of them, then you can find multiple stratum 2 servers that are syncing their client, that are getting their clock from the stratum 1 server, and when you're typing in your Linux machine NTPQ minus Q, for example, then you can see which NTP servers you're using. So it's quite straightforward. So the recommendation is authentication with SHA-1. No one really does this. However, I have couple of enterprise customers that are using NTP in a completely unsecure manner. They simply use servers, and you have typed in ntp.pool.org, pool.ntp.org, and you're fine. I do not recommend this, because you have anyone who joins this pool can place in their NTP server, which is okay for your home connections, but not for your enterprise, where you have time-crucial services, and they're not using authentication. So NTP itself can use authentication via MD5 and SHA-1. Please use it when you're an enterprise. So please buy a NTP appliance who gets its clock from one of these external sources and leverage NTP authentication. So the challenge, what's the reference ID from the IPv6 NTP server? So there's only one IPv6 client server communication with IPv6. All these others are for IPv4. So what's the reference ID? Yeah, exactly. DCF-A. Yeah. So here it's DCF-A. DCF stands for the German DCF77, and A means amplitude modulation. You can also have DCF-P for phase modulation. Okay, since we are running a little bit out of time, I will skip a little bit. Simple network management. Again, you can manage your devices. You can get or set variables for management stations. So you have a network management station. Mostly it's used for interface and CPU memory stats for classical routers and switches. So it's using UDP port 161. You can also send traps. And by default, it's SNMP version 2C, what is used really everywhere, but again, this is plain text. So recommendation is clearly to use SNMP version 3, which has encryption and authentication. Because, for example, you can not only get interface statistics, but you can also get logged in users, routing tables, and whatever. So whenever you're using it in plain text, it's not a good idea. So the challenge, what's the used community string? So the community string is something, you must not read it out completely. So the community string is something to distinguish the SNMP tree that you're able to read out, but it's here in clear text. So what's the community string? It's starting with? Yeah, exactly. Thanks. Sorry. Okay, so click in the Wireshark precap, you will see it. And this is the last protocol for today. That's the trivial file transfer protocol. It's FTP, which is unencrypted, even more trivial. So no authentication and completely plain text, which is not good at all from a security perspective. It's using UDP port 69. The common usage for all the devices is, for example, a configuration files backup. Nowadays, I would recommend it. The recommendation is don't use it at all. You should use something like SCP for backups. So the keyword is information gathering. Challenge, what is the hashed password of the user Weber? What is the hashed password? So when you're looking at TFTP, then you have one stream. You can follow the UDP stream. Then you have a completely Cisco router configuration. And here underneath you have a find. You can type in Weber, because that's my normal username. Anyone already having the hash from the user Weber? Yeah, exactly. So when you're searching for Weber, then you're getting a statement, username, Weber, privilege, This is the hash password. As I'm using quite easy passwords in my lab, you can simply brute force it because you will find the answer in a couple of seconds. So last Snickers, who was it? You already have one? Who won? Yeah, you can give it away by yourself. Okay, so all 10 challenges, all 12 challenges, you've managed to do 12 challenges. Who has won a Snickers, by the way? How many people? I think it's 11. Wow, cool, so thanks for participating. So what's the security conclusion, or what's the conclusion at all? Use encryption and authentication for your network management protocols. Avoid plain text protocols. Expose your network carefully. So Of course, you have advantages for all of these protocols because they are easy to use and you have some functionality, but please be aware that a passive attacker can sniff your packets. Take your own PCAPs and have a look at them at home, at your enterprise, whatever, and you will see that these protocols are really used. These are the protocols I've not covered, which are still a lot. Resources, there's an IPv6 bus podcast where there's a session called Understanding and Troubleshooting IPv6 with Wireshark, where you have some more information. You will get the link. I have a packet challenge. Yeah, thanks for that. If you have any questions, please come to me, send me an email. And yeah. And finally, I have some stickers for you because I really like those acronyms. It's a kind of a bullshit bingo. So this is the networker's acronym paradise. It has about 400 different acronyms. So please take away those stickers. I have lots of them. Please hand them out. Take as much as you need. And I have another sticker. It's called IPv6 No Nut Anymore because I'm a fan of, it's always these nuts IPv6 discussions. So please take the stickers if you want.